Hey, I'm Paul. I am one of the founders of Unison Computing. Today I'm going to be talking about how you can use Unison Cloud as a new kind of typed remote procedure call middleware. This is a really cool set of ideas that let you get a lot of the advantages of microservices without the usual drawbacks of microservices. And it is something that can have a huge impact, especially at larger organizations that have lots of services communicating with each other. And I think the really cool aspect of it is that this is something that can be incrementally adopted. You do not necessarily need to rewrite existing services in Unison to start getting many of the benefits of this approach. So let's get to it. So what's the problem we're trying to solve? Microservice complexity is a huge drain on many organizations. You have all these different services. They need to be packaged up and deployed. So it's sort of operationally pretty complicated compared to a monolith. And there's also the service call boundary where there's a certain amount of complexity of, you need to encode and decode at that boundary and do some networking to get the service call to happen. And so this kind of thing has led a lot of organizations or a lot of people to kind of feel like, oh my gosh, these service-oriented architectures, it's just not worth it. We should go back to the days of monoliths and build systems that way. But I think that's not a good idea. Microservices were adopted for some very good reasons. They have some pretty big benefits. So probably this first one is the most important one on the list. It's that microservices really nicely support separate deployment. So you can have different teams that are developing new versions of the services that they maintain and deploying them independently without coordinating. And it sort of is transparent to the rest of the organization. You don't have downtime as new service versions are being released. And this is something that you kind of just get out of the box when you are building things the microservice-y way. You also get separate permissions. So it's nice that a service is something that you can assign different permissions to, different secrets, database access, whatever it is. You often don't want all the code in your application to be able to, access like the Stripe API key or some other important secret that you want to be more tightly controlled. And so services give you that. They give you that sort of separate permissions assignment. And there's a number of benefits to microservices, and these things have been achieved, but they've been achieved by inserting a network boundary, and that has a huge cost. So it wastes latency. So it might be 3 to 10 milliseconds at a minimum to even just make a service call that's doing very little, because you have to open up this network connection. You have to parse and serialize whatever the arguments and results are. And so there's some latency and compute that's being wasted there. And then there's developer time. So there's some code that needs to happen at that service call boundary to ultimately send bytes over the network and parse bytes that are coming back. And that needs to be specified somehow. Even if you're using a sort of RPC framework where you're like generating code for that boundary, that is the specification for that code generation is itself code that needs to be written, it needs to be maintained, it needs to be kept in sync with all the call sites, and that becomes a whole thing. So the dream would be that we get the benefits of microservices without the drawbacks. So I like to imagine you have all these smart people working at the company building all this different functionality, and imagine if it's more like a library of code where if you want to access some functionality, it's just everything's a function call away. There's a common type system to make sure you call the function correctly. You have a real programming language at this level where you can define new functions, new abstractions, compose different services, and it's like writing local code. And so in this world, you could define new services, new automations, batch jobs, and it's like local code. I think that's the feeling you want at the level of not just an individual service, but at the level of things that talk to many services. That's the dream. Okay, more specifically though, we want a few other things. We want easy incremental adoption. We don't want to have to rewrite everything in Unison. We don't want to have to touch existing services if we don't want. In terms of supporting separate deployment, it's important that callers get the latest version of the service. So if a bug fix is made, the callers of that service get the new version without any sort of explicit action on their part. So it's kind of just a transparent upgrade, at least for things that are backwards compatible. If there is a breaking change to a service, what you want is that the new version of the service is something that people have to explicitly update to. Obviously, you don't want to transparently update to something that has a different signature and then nothing works and it just explodes at runtime. You don't want that. So you want sort of the old version of the service to stay around, and then different teams will upgrade at their leisure to point to the new service, and it'll be a nice typed refactoring, just like refactoring local code. Lastly, I think it's important to support garbage collection of old service versions, so we need to know, when a service is no longer referenced by anyone, and then it can be undeployed. Okay, so that's a dream. Okay, here is a big idea that we're going to make use of to achieve the dream. It's part of achieving the dream. It's called adaptive service graph compression. So if you look at a traditional service call where there's a network boundary there, the reason that there's a network boundary, and one way to think of this, is that services are immobile. So you have the caller service running, say, in one container, and the callee service running in a different container. And traditionally, you can't just move code between containers at runtime. Services can't just be on the fly moved from one place to another. That's not a thing. And so what we do instead is we send the data to the code. We send the argument to the service to the service. In Unison, we get to do something different though, and this is pretty cool. In Unison, code can just be dynamically relocated. That's sort of the superpower of Unison, is you can move code from one place to another without dependency conflicts on the fly, and this is just no big deal at all. And so in Unison, the model of service calls is different. We actually bring the service code to the caller, and in doing so, we eliminate the network and latency and encoding and decoding that would otherwise happen there. Okay, so kind of a neat idea. It's called adaptive service graph compression, and the reason is, if you sort of think about what this is going to do, it's like if you have a service graph like this, where you have all these things calling all these other services, whenever you make a call, what Unison Cloud is going to do is, instead of that being a call that has to cross from one place to another, it's like it's temporarily squeezing together those 2 points in space, because it's like basically bringing the code of the callee to the caller and caching that code there. So if you make repeated calls to a service, it's going to keep that connection. And so it's like the overall service graph is adaptively kind of reconfiguring itself and moving places, points on that graph close together or next to each other to minimize overall network latency. So it's this very adaptive, flexible thing that you could basically never achieve, any other way. But we're now just kind of getting it for free, just through the ordinary kind of dynamic code loading that Unison Cloud supports. And this is something you can only get with Unison. So that's adaptive service graph compression, and this has a huge impact on overall latency of a system, because essentially in the fast path where the code is already cached for a service, you don't have any network latency or serialization happening at that call boundary, and it's basically just like a local function call. So super cool idea, adaptive service graph compression. And this kind of speaks to the model of services actually being a little bit of a different thing in Unison Cloud than with traditional technologies. Okay, so I'm going to get into a little bit more practically just sort of how an organization can work with Unison Cloud and support this nice typed RPC experience across the organization. So I want to first review just kind of the basic type signatures of how you work with services on Unison Cloud. So there is service hash AB. It is a remote function from A to B. It's identified by a deterministic hash of the function that you pass to deploy, and also the environment, which controls secrets and database access and permissions for the thing that you're deploying. So the environment and the function, they're hashed, and that determines the service hash AB. So notice it is service hash AB. It's typed. So it's not like, just like a URI and then you send it untyped blobs of JSON. It's an actual typed, a reference to the service is a typed thing. And when you call a service hash AB, you have to give it an A and you get back a B. Pretty simple. A service name AB is like, it's also a typed reference to a service, but it's by name instead of by hash. And so the way you create one of those is just by picking a textual name that returns a service hash AB. And then the key thing is that you can assign a service name to point to a service hash. So you can think of this maybe a bit like a get branch can point to a get commit. Okay, and then you can of course call a service by name, and that will resolve that service name to the latest service hash and call that service hash. Okay, so a typical declaration of a service is just going to be a service name declaration that you give a type signature to. So you're going to make up a name for the service. I recommend putting a version number at the end here for reasons that I'll explain in a minute. And you say service name.create, and you give it a type signature. So this is the album service. It's just going to be mapping a song to a list of albums that song appears on, say. And then elsewhere at a usage site, you are just going to call that service. And you're going to be calling it just like this, a single line of code. There is no network boundary happening here. It's going to be doing that adaptive service graph compression thing. And you don't write any serialization code, and you're not paying for a serialization or encoding and decoding. So it's basically as fast and easy as a local function call. I mean, not quite as good as a local function call, because there is a bit of, when you call a service, it needs to run the invocation under the callee's environment. So there's like some little bit of a context switch there, but it's still much more efficient than, actually serializing things and sending them over the network. Cool. So another really cool thing that you would not necessarily expect, but you kind of just get this for free with this approach, is that service calls kind of support batching in this automatic, nicely adaptive way. So here is like a loop where we're calling list.map, and we're fetching the thumbnail for each of the albums that was returned from this first service call. And like ordinarily, if there were a network call here, this would be a very silly way to implement this, because it's going to be like making, a bunch of separate network calls in sequence. But with the Unison Cloud model of services, the fast path is just that there's no networking happening here at all. And even sort of in the worst case, you might suppose the thumbnail service was not already cached at the current node. Cool. The first time through the loop, it gets loaded from storage and cached, and then all the subsequent times through the loop, we're just hitting that local function essentially. So this is a lot nicer than what often happens at organizations, which is that they introduce kind of batched versions of API functions in a very ad hoc manner. And with this approach, it's kind of like you don't really worry about that. You just kind of write the service in whatever way is the most natural, and don't worry too much about the batching. Okay, cool. So here is the basic idea for how an organization can actually work with these service names and service hashes and maintain this nice library of services that can all be called with a common type system. Okay, so we're going to have one. By the way, this is one way to do it. There's kind of other ways that you could get even fancier than this, but I think this is like a simple way that would work for many organizations. The idea is you're going to have one service registry project. And all this is, it's going to be just a number of top-level declarations of service names. And each of those service names is going to have a type signature. Cool. So the other thing that might be in the service registry project is any common interchange types that are used as part of the public interface of services, different services. So there might be like a song type, or the album type is something that lives in the service registry project because it's actually part of the organization's common communication protocol that's used for talking between different teams and services. Okay, so but pretty basic is, essentially it's going to be a library that consists of a bunch of boring service declarations like this, but they have type signatures. You might also put docs. That would be another thing to put in here, is documentation for this service, and you could use Unison's rich documentation support for sort of giving examples of the API and so forth. Okay, all of the other projects at the organization are going to depend on the service registry project. And how do they do that? It's like literally just like any other library dependency. So you're going to lib.install myorg/registry, and it's just like any other library reference. You'll refer to definitions there. When you need to upgrade it, you will lib.install again and do an upgrade, easy peasy. And now anyone at the organization can call any service in the registry, type checked, and it's a single line of code. So I can call the album service, I can pass it the song Cruel Summer, and if I try to pass it an ice cream cone, I'm going to get a type error at compile time, and you don't write any serialization code, and it's great. Now, teams can deploy new backwards compatible versions of services just by calling deploy, and so you can always do that. You can always call deploy with the function AB, you get back a service hash AB, and then they are going to assign the service name that is declared in the registry to point to the new service hash. Now, they probably should maybe run some integration tests against the service hash before doing that assignment. That's actually something that could even be automated. So you could have a sort of conditional deploy, which is almost like a CI process that you would just write ordinary Unison code to manage. And of course, you can support rollbacks. You could assign something back to the old version of the service, and so forth. You can even do fancy things like A/B testing, and all kinds of things you could just do with sort of writing regular Unison code. But okay, so there's this independent deployment happening. That's great. If new services are introduced, that's also great. You just add them to the service registry project and cut a new release of that project, just like you would any other library. Now, what about backwards incompatible changes? Well, here's how that works. We are going to basically add a new service to the registry, and then users are going to manually upgrade to that new service. So this is just a suggestion, but I suggest you might take the old album service and rename it to album service v1. This doesn't break anyone. This is just changing the name that's associated with this definition. So that still, everyone can still continue calling album service v1. And then you introduce the new album service, which is going to be album service v2. Maybe it has an extra parameter, a quux. It takes a quux as well as a song instead of just a song. And maybe you give the latest version of the service the good name rather than putting version numbers on every service name. And then what do downstream users do? It's easy. You would cut a new release of the service registry project. Users would upgrade to that, and then at their leisure, different teams would switch to the new version of album service. Okay, and they might do that with all in ordinary nice support for doing typed refactorings. In Unison, you might ask for the dependents of the old service, album service v1, put all those in the Scratch file, and then get that Scratch file compiling to point to the new album service. And it's a typed refactoring. You have the type checker telling you where you've missed, oh, you didn't pass a default quux here, and so forth. You might even get the support of Unison's structural find and replace. Unison has actually this nice capability of doing structural rewrites to code, so you can find and structurally rewrite code without doing text munging. And teams that are producing backwards incompatible versions of services might publish in the service registry some rewrites that could be used by other teams to find and upgrade code to the new version of the service. Cool. So now in terms of garbage collecting old versions of services, well, Unison and Unison Share, we have a perfect knowledge of the dependency graph of your code. And so, we can detect when a branch of a project is, no longer referencing, say, album service v1. And so once you know that everything is no longer referencing album service v1, it can be undeployed. Now, one thing I do want to say about undeployment is the model of services is different with Unison Cloud. It's not the case that, when you deploy a service, it's just always running on a container and occupying resources. Instead, I would think of it more like there is just this compute fabric that exists. Any node in that pool could be running the code of any service, and that compute fabric exists, and just dynamically we are loading the code for services onto that fabric or different nodes of that fabric and caching it. And eventually things will expire from the cache and nodes will get recycled and so forth. But it's basically doesn't really cost anything to have a service deployed. The only thing that we need to keep around is we need to store the code of that service durably so that, if at some point in the future a service request comes in, we need to be able to load that back into memory on a given node so that we can, start serving requests for it. So anyway, it's not a huge deal to keep services deployed. The reason to maybe undeploy services is more of a security thing, or like if you deploy a super buggy version of a service that you never want anyone to call, then you probably want to undeploy it so it doesn't get called accidentally, say. But it's not sort of occupying a lot of cloud resources to just have a service deployed if it's not being called. Okay, cool. So what about incremental adoption? So this all sounds great, right? But not everything is written in Unison, and so how can we still get some of the benefits of this approach while leaving existing services alone? And here is the trick. It is to take an existing service and wrap it in a Unison proxy service. So a Unison service can do anything. It can have a bunch of code in pure Unison for implementing the logic of the service, or it could make HTTP calls to some other service that's written in, Go or Scala or Rust or whatever. And so you can write a proxy service like this, and you might even use code generation to help produce these proxy services. And the nice thing is that now you have taken that service and wrapped it in a nice typed interface. So now in Unison land, you can interact with this service and you get this nice type system to mediate the process. And so what have we gained? Well, we have done something kind of interesting. So this is a little bit subtle, but I'm going to try to explain it here. So services, the reason they exist is because they are reusable bits of functionality that are called in multiple places. That's like why they were sort of factored out into a service. So they're like functions in that respect. And right now, organizations have this sort of boilerplate and this complexity at each of the N call sites of a service. But as soon as you wrap a service in a Unison proxy, you can define as many users of that service in Unison land as you want, and none of those call sites are going to have any boilerplate at all, because they're all just going to be interacting with a nicely typed proxy service, right? And so you can start defining new services in Unison land. You can maybe start even something lower risk like integration tests, automations, and you can do that in a few lines of Unison code, and it's like the Unison experience of just kind of writing code as if it's single machine code that's talking to all these services as if they're just library functions, and you sort of get that experience even just if you wrap a collection of existing services with these Unison proxies. And so I think this is really interesting. And I think there's almost two kinds of services that exist at organizations. So there are services that they're doing serious computation, or there's something computationally very interesting about what they're doing internally. If you have like a video transcoding service or something like that, those make sense to be written in whatever language is best suited for the task. Keep those as is. But then there's this other class of services which are more like glue services, I call them. And these are also very common. It's like, you might have a service that has to call 6 other services and combine their results in some way. There's like a little bit of computation happening, but it's like not anything like video transcoding. It's more like just implementing some basic business logic. And this is super common. And my feeling is that glue services like this they're really best written with a technology that's at a much higher level of abstraction, that supports very easy cross-service communication, that has a super nice type system, common type system. And it's much, much nicer to write glue services with that kind of technology, because you really can just focus on the business logic and not sort of all this plumbing code of just getting things to communicate. And so I think that's where Unison can work really well. And I want to make an analogy of sort of in the games industry, there's this split between the game engine, which is super high performance and it's written in C++, and then there's large chunks of the game logic are written in these much higher level languages or DSLs, and sort of for good reason, because you just don't need all that stuff to be written in C++. And I think application backends are kind of similar, and I think that if an organization begins adopting Unison Cloud and using it as this typed middleware, it is something that provides this common type system for all of the functionality across the organization, and it lets you sort of script and assemble in a very compositional way pieces of functionality that are developed by large numbers of people who, at different teams at the organization. And it's like this higher level DSL or scripting language for your entire organization. And that's what Unison Cloud can become over time. And that's a really powerful thing that doesn't really exist right now. So right now, what exists is sort of these more lowest common denominator protocols for talking between services and building distributed computations. And Unison can offer something that's higher level. So cool. That's it. I hope that you enjoyed that. I have some appendix topics, but if you just click through the Notion document, you can explore these. But I hope that you enjoyed. Thank you.